Okay, so now we're going to take a look at something a little bit different. I started getting out some of the equipment that I've set aside for this. Ooh, don't want to knock that over. Okay, we'll get to that here in just a moment. Now, we've talked a little bit about applying Ohm's law. There are a couple of videos on that, and hopefully that one's pretty straightforward. Now we need to talk about a concept called power. Now, we've learned before that energy is an incredibly awesome way to look at complex systems and figure out what's going on with them and make predictions on them as well. The thing about circuits is we're not going to be looking at energy in and of itself because things are constantly, well, not necessarily constantly changing, but everything is moving. And so one of the things that we're actually going to be looking at is power, which, if you remember from last semester or the beginning of this semester, depending on when you covered it, power, capital P, is equal to the energy divided by the time. So power is what we look at specifically with our circuits. So for instance, let's go back a little bit and talk about some of the things that we work with, and it's going to help us put together the power equation itself. So delta V, our potential difference, that's the thing that keeps the circuits moving. It's related to energy, but it's not fully energy itself. In fact, I said that delta V is measured in volts, and a volt is equal to a joule per coulomb. So it means it's energy per charge. It acts a lot like a height, where height gives us some information about gravitational potential energy, but we don't know how much energy we have until we know about the object we're putting there, the mass for gravity, or the charge for electric potentials. But a volt is made up of a joule per coulomb. And the other thing that I mentioned, one of the other key things that we keep track of, is the current, which is measured in amp, which I told you was a coulomb per second. So this is where our charge comes in. If I were to take a volt times an amp, I would get the following. I would get a joule per coulomb times a coulomb per second. Now you may see that the coulombs cancel out and we're left with joules per second, which is energy divided by time. This is better known as a watt. I apologize, I'm filming in my kitchen. Quiet you, I'm busy. All right, this is a watt. In other words, this is a unit of power. It's hard for us to get energy by itself because instead of looking at one individual charge, we're looking at how many charges go past a point in a given time. That's the idea of current. So we can still apply the ideas of energy and energy conservation onto circuits, but it's easiest if we go through and look at them at how quickly we're transferring that energy, which is power. This is also why when you talk about circuits or electrical things, you talk a lot more about powering them as opposed to the energy. I know when we first covered energy, that was something that was a little bit confusing. I mentioned that you're so used to using the word power and the idea of energy interchangeably, but they're different things. Well, this might be part of the explanation as to why. All right, so that's a little bit on the units. In short, hopefully, that helps you see the most basic form of the power equation, which says the following, that P, our power, is equal to delta V times I. Now, I've also written it before. In the past, I didn't have delta V, I had P equals IV, or P equals I delta V. But this is kind of the logical way of writing it. One isn't better than the other. I should be more careful with what I say. But if we take the electric potential difference and we multiply it by the current, that will get us the power through whatever component we're looking at. So if the potential difference is one thing and the current is that through it, then we multiply those together. Now, there are a couple things that we can do. I can also take the following. Since delta V equals IR, that's Ohm's law, if this is delta V, then I can always plug in IR, and that would give me IR times I, where this is delta V. So P also equals IR times I. P also equals I squared times R. You can also do a different replacement where I equals delta V over R. I'm reworking Ohm's law here. If this is I can always plug it in here, and I would get the following. delta V squared over R. Now, I don't expect you to have all of these memorized. What I'd recommend is being familiar with the first one, P equals IV or I delta V or delta VI, however you want to keep track of that. You can think back to the units that I just showed you. But something that can be very useful in this is keeping in mind, I always introduce power as having three different equations. That you have the power is equal to our current times our potential difference, or it's equal to our current squared times the resistance if we're dealing with a resistor, or it's equal to the potential difference squared divided by the resistance. All three of these are good equations for DC circuits for finding the power. All right, let's take a look at a little bit of this. First and foremost, one of the things that I like to bring up on this are connections to real life. So I've got a charger here. I use this to charge my phone. Now, you can grab your own and actually take a look on there. I've got, let's see, you're looking on the back, it says input and gives you a string of numbers. What you're looking for is output. Now on mine, it says that for the output, I have something that is marked 5V. Well, what has units of V? Volts. That's our potential difference. This is the potential difference supplied by this charger. All right? It outputs 5 volts and 1 amp, 1.0, oops, 1.0 amp. That's going to be our current. So I can actually find out what the power supplied by this thing is. I can do the following. P equals I delta V or delta VI. Sorry, I kind of go back and forth. I think I'm more comfortable with I delta V. That's how I had always learned it. So I may start writing it that way. But it's multiplication. Order doesn't matter. So P equals I. So I'm just going to write this in even without the colors. 1.0 amp times 5 volts. And I get the following. That this is a 5-watt charger. That's the power that it has to charge things. Great. How is that different? Well, here's another one. This one belongs to a friend of mine. And it actually has 2 ports. One says 1 amp and the other says 2.1 amp. So let's take a look at that. It says that its output is 5 volts at either 1 amp or 2.1 amp. Well, we already know the first one, the one that's marked 1 amp, is a 5-watt charger. Many of the chargers that you have are probably going to be standard as that. However, they have a second one on here that says that its current is equal to, I think this marker has to warm up some, 2.1 amp. Hopefully you can see that pretty clearly. Let me see if I can get a darker color. I got some new markers for this just so I'd have some. Current is 2.1 amp. Okay, so if I were to find the power on this one, power is going to be equal to, we said that it is 2.1 amp this time, times 5 volts. Well, I multiply those out and I get, what, 10.5? I'm going to double check. 2.1 times 5, 10.5. 10.5 watts. Now, the idea behind this is, some of you may even have these, they're quick chargers. This one will actually charge your devices faster. Be careful using that because some things don't react well to having more power than they're designed to have go through them. Let's check a couple of others. I've got an old charger for a camera here, one of my old cameras. In fact, I used to do videos with this one. It says that it has an output of 5 volts and 650 milliamp. So we've got delta V for my camera is 5 volts. You'll see that 5 volts is a pretty common supply. In fact, you'll notice that they've got these USB connectors. Most USB connectors are designed to be 5 volts. Not all of them, but many of them. Okay, so the output, they said the current for my camera was 0.650 amp, 650 milliamp. I told you you'd see milliamp a decent amount. So the power for my camera charger is going to be 5 times 0.650. We end up with 3.25 watts. Great. Let's take a look at one or two more before we're done. Okay. I've got a laptop charger here. This one, you can imagine, hopefully, is probably going to supply a lot more. Its output, let's go back to the brown. So for the laptop, we've got a marked output of, hey, look at that, 19.5 volts. This isn't a USB connection, so it might change things up a little bit. 19.5 volts, and our current that it has listed is 4.62 amp. Now that's a lot of current comparatively. We can then find our power by taking 19.5 times 4.62, and this comes up to no great surprise, power of 90.09 watts. In other words, it's a 90-watt power supply. Now, as you get to larger and larger computer devices, you're going to end up with more and more of that. So in a standard desktop computer, for instance, they have a power supply that is about somewhere between 200 and 300 watts. If you want to have a fancier game system, those of you familiar with desktop gaming, it's more common to need a 600 to 700 watt power supply. Some of you may even have over a kilowatt, over 1,000 watt power supply. And part of that is because you need more power to get things done. Now, quick takeaway from this. For these chargers, one of these is a regular charger and the other one's a quick charge. So you can see that we get 5 watts. That means every second this gets 5 joules. With the different one, the fast charger, every second it gets 10.5 joules. You get more energy faster, and energy is what we're charging into these batteries. That's what we're actually filling them with. So these will charge your phone much faster. The standard output on a computer USB port is, let's see, let me clear some space here. I think we're pretty much done with that. For a standard computer charger, or a computer port, they've got delta V of 5 volts, and for a standard computer connection, at least for a while there, the limit was 0.5 amps, 500 milliamps. You multiply these through and you'll find that the standard power is 2.5 watts. In other words, it'll take 4 times longer for me to charge my phone plugging it into the computer than it would using, say, the quick charger, because I get 2.5 joules every second, whereas with the quick charger I was getting over 10. So in case you've ever noticed why when you plug things into your computer, they'll charge, but they charge much slower, that's because of the built-in limitations of the computer ports. Great. Let's connect this to something else and maybe answer the question that you may be asking yourself, well, what gives, computer? Get with the program. I need my energy and I need it now. So let's take a look at how we can connect this to materials that will show up in my class and are likely to show up on the AP exam. So I've got a simple circuit pretty much right here. I've got a power supply, my batteries, and I've got a light bulb here. So here's what I'm going to do. I'm going to set this up and we're going to take some measurements. First and foremost, let me bump this over to DC volts. Wake up, meter. There we go. I'm going to take a quick measurement. This thing reads 3.23 volts. So for my simple circuit, I've got a potential difference across the battery of 3.23 volts. Great. Now that's a little over 3 volts. These are real world batteries, so while it's supposed to be 3 volts, we're going to have a little bit of fluctuation. All right, here's what I'm going to do. I'm now going to switch this over so that it can measure the current. That's the nice thing about this device. It's a digital multimeter. It can measure a bunch of different things. In fact, let's play on the safe side, because I don't know right offhand what the resistance of this is going to be, and I don't want to blow out the fuse on my DMM. So here we go. Here's what I'm going to do. I'm going to connect one side here, and I'm going to connect it over here, completing the circuit, and here we go. We can see the light come on, getting a measurement of the current. The current that I get, at least as far as I can measure, is 0.18 amps. Current equals 0.18 amps. Great. So that's my current, and this is my potential difference. Great. Let's go through and quickly find, let's see what the resistance of this light bulb is. Let's apply Ohm's law real quick. So we know that 3.23 volts will be equal to 0.18 amps times our resistance. Therefore, our resistance is going to be 3.23 divided by 0.18. We end up with approximately 17.9 ohms. Okay, so this right now appears to have a resistance of about 18 ohms. We're going to see if that changes. Let's see what the power is for this thing. Okay, so our power, we said, was equal to our current through the light bulb, which is going to be 0.18 amp, times our potential difference, which should be pretty much the 3.23 volts that we see for the entire circuit. I multiply those out, 3.23 times 0.18, and I end up with 0.581 watts. Okay, that's about half a watt. Okay, watch what I'm going to do. I'm now going to take and put in a second power pack. Now, don't necessarily try this at home, but let's get an idea of what our new potential difference is. I've basically changed the batteries that are powering all of this, and I'm going to check the whole thing here. Oh, I have to switch this out. Remember how to use your meters, Sanchez. Here we go. Now it's bouncing around a little bit, but I'm getting about 6.3 volts. I'm going to switch this out, different color. Delta V, about 6.3 volts. Now it was fluctuating a little bit, so we might end up just a little bit off on some of our rounding error, but that's okay. I'm going to go back up to my 10 amps so I don't blow my fuse, and here we go. Now we've got a current of 0.26, but I want you to notice, take a close look at that light. In fact, comparing it, watch. So there's the light with one set of batteries, and here's the light with two set of batteries. What do you notice about it? All right, let me double check what my current was. 0.26, 260 milliamp. I equals 0.26 amp, which is 260 milliamp, at least to the precision of this measurement. What did you notice about the light bulb? Well, hopefully you'll notice, now this is pretty easy to look at, and this is much harder for me to look at. It got much brighter. We're going to come back to that in just a moment. These are older Edison-style light bulbs. They're the incandescent bulbs that many of you are probably familiar with. Real quick, let's see what we've got on our power. So our power, P equals I delta V, so I'm going to take 0.26 times 6.3, and I end up with, we are now at a whopping, comparatively, 1.64 watts. I pretty much tripled the power going to this light bulb, and it got much brighter. Something to think about. We went from about 0.6 watts up to 1.6 watts, so we had an increase almost triple by doubling the power pack, the potential difference. Now, one of the things to note on there is, well, why didn't it just double? I doubled the potential difference. Well, you'll also notice that our current did not stay the same, and you're going to hear me say this a lot because this is an important thing to remember. When it comes to circuits, if you change even one thing, there's a good bet that everything changes. So, sometimes, once we get to the later parts of this section, when we start looking at changing circuits, you're going to have to think a lot more thoroughly about them. Real quick, let's double check our resistance on this. Well, so let's see, V equals IR, so we'd have delta V, 6.3 volts equals 0.26 amp times our resistance. Our resistance this time that we are finding is 6.3 divided by 0.26. 24.2 ohms. That's weird. That's a noticeably different value than the 18 ohms we had before. That's something to keep in mind about light bulbs. We're going to treat resistors as though they are light bulbs because they're easier to imagine that way. But light bulbs do not always maintain the same resistance. It depends on how much you connect them to. They can actually fluctuate some. That's why what we'll actually be modeling are true resistors. That being said, let's keep going. Let's add a third power pack. Now, I told you all not to do this sort of thing whenever we're working with the lab equipment, and I think we're about to find out why. All right, first, let's get a measurement of our potential difference, because I think I know how this is going to end. Well, let's see. Oh, helps if I set it to the right setting. There we go. 9.67 volts. So delta V is 9.67 volts. All right, here we go. You might not want to look directly at the light bulb. We have now upped the power yet again. Let's see what happens, though I think I know. Yep. You see that flash? Watch. This is why I told you not to do this with the circuit equipment. That flash was the light bulb burning out. This thing's now trash. Oh, sad face. This is why I don't want you to do it in class. You've seen it here. You can rewind it, watch it again. It's great. This is also why we set up different things. So, for instance, that's a 1,000 ohm. In fact, let's talk a little bit about this. I don't think the 10 ohm is going to do it. Let's take a chance on a different light bulb. I think these will be fine, and I got a whole bag of the easier to replace light bulbs. I really should have put one of these in the first place, but figured I'd let you see what it looks like with the bulbs that you're familiar with. All right, here we go. So, on this one, we could do something similar. Now, we could redo all of these numbers, but we're totally not going to. I can then connect this. It's pretty bright. This gets much brighter. And if I connect this, I don't want to burn out yet another bulb. But watch what happens when I do the following. I'm going to put a resistor in here. Well, that's weird. Pretty much nothing. Maybe my resistor's bad. Oh, let's try something, shall we? I am getting a reading. I've got about 90 milliamp. So we do have stuff going through, and in person, remind me, I can try and set this up. There's a very dim glow coming in. Let me see, where did I set my kits? Give me just a moment. I think I'd be better prepared for this. That's okay. Let's do an additional power pack. I didn't think that I'd need more than 3, but here we are. I've got a 100 ohm resistor. I am low on some of my parts, so I'm going to put this here, put this here. There we go. Let's see if the additional power pack makes a difference. Oh, it does. And if you look real close, though, it's going to be hard to see. It is starting to light up, and I've got 11 milliamp. Let me try one more power pack. But after this, I'm giving up. This is why I told you not to go with too many power packs. And if you look back at the video that I did on Ohm's Law, I mentioned that we had to put a resistor in to control how much power goes to it. Now, you already saw that if I just take these 3 and connect it to these light bulbs, they burn out instantly. But if I put a resistor in, which will change the amount of current that goes through, you can now see that the bulb lights up just a little bit. We're up to 13 milliamp on this. Now, we could go through and start solving this, but that's what we're going to do when we get to the more advanced stuff, because now we have a resistor here and effectively another resistor here. And ow, I just burned my hand. Okay, so let's talk about that too. We're talking about energy going somewhere. Now, the batteries are giving off a decent amount of energy, and they're putting them into things like lighting up the light bulb. Resistors will take them and put them into thermal energy, into heat energy. They'll actually heat up. But this is what a resistor is supposed to do. It's supposed to go through and control how much power gets out to something so that you don't overload them. So for instance, I set this here and it no longer lights up because it's burnt out. We can see here, this one's working just fine, and this one is also working just fine. The resistor is used to control how much power goes out to it, so that we don't damage the equipment. Most equipment is designed to be used in a given power range. That's why I tell you on some of these quick chargers, be careful with them. Anytime you use them, they may be above the regular rating for your device, and while they may not burn them out like a light bulb, they can damage them, which can lower how long that battery will work. Now, I don't mean to say that all of the quick chargers are suspect and you should avoid them, but please be knowledgeable about that. It's part of why we study circuits, so that you all can get an understanding of the things you use on a regular basis. I've got equipment that, honestly, this camera that I mentioned, I've had this for over 10 years at this point, and it's still working just fine, mainly because I'm very cautious in how I use the equipment that goes along with it. All right, so this is a brief rundown on power, how we can find it. You can also go through and use these equations. If we only had the current and the resistance of the resistor, you could plug those in and get the power that way. Same thing with the potential difference and the resistance. I'll have a subsequent video where we talk a little bit more about that.